So you have an overview of all these tests on this slide. As I kind of flagged this slide as being quite important to keep an overview of the respective tests. So when doing an ANOVA, you are now comparing, building a ratio between the variance between the groups and the variance within the groups. But basically estimating the variance between the groups, that's the deviation from the grand mean, which is the mean of means, divided by the variance within the groups, which are basically the variability within the groups from its respective group mean. We're distinguishing two types of variance, a between groups ANOVA and a within groups ANOVA, where basically the between group ANOVA compares each individual group mean from the other group means. The within group ANOVA has basically the same purpose, but it's basically employed when you have the same participants going through each level of your independent variable, meaning you get some of this variability explained by the variability that is inherent to the differences between the subjects. By being able to subtract this, you basically get a different and smaller within groups variance that will allow for you to possibly get a larger F score, thereby get more reliability and less variability in your estimate. And by that, essentially, you will have a more accurate hypothesis test. So the types of ANOVA, you basically have a one-way ANOVA when you have one scale-dependent variable. If you have two nominal variables constituting the independent variable, you will have a two-way ANOVA and three-way and four-way and five-way. So that's basically how you continue. Between groups, you're basically comparing the groups with different participants in each group. Within groups ANOVA, you have and the same participants undergoing different levels of your condition, which is the independent variable. It's also called a repeated measures ANOVA, so keep in mind when you're confronted with a different terminology. The assumptions are basically, as for all other hypothesis tests, is a random selection of samples, and since we're dealing with parametric tests, a normally distributed sample. And lastly, the so-called homoscedasticity, distinguished between homo and heteroscedasticity, where homoscedasticity stands for an equal. Homo means equal in Latin, no Greek. And you have a variation that is less than 20% in the variability between those groups. So it's a comparable variability amongst all groups. The steps of hypothesis testing are the same for the ANOVA than they are for the other hypothesis test. The key is really that the critical value is now, so when you calculate your test statistics, you're comparing this in hypothesis testing against a critical value that we have read from the F score table. So you're calculating an F now rather than a T or a Z, and you're comparing this F against your critical value. Remember, the F score table basically has two axes. So one basically that goes horizontally, it constitutes the number of groups. That's the so-called numerator, and the rows are basically the denominator, so the number of degrees of freedom amongst all groups. You estimate, and then you compare this against your critical value, and then you will determine whether your null hypothesis is being accepted or rejected. Where your null hypothesis basically is that all the group means are the same. If you come to reject the null hypothesis, you assume that at least one group is different from one other group without knowing which one. And that's essentially what we have to continue today, because we stopped at post hoc testing last time. So null hypothesis, degrees of freedom is simple to determine. You basically have degrees of freedom between, that's basically the number of groups minus one, for that redundant, if you know the sum of squares and the variance. The degrees of freedom within is basically the group degrees of freedom of each individual groups. So that's the group sample size minus one, which can be unequal for between groups ANOVA. Also keep in mind for the quiz, the degrees of freedom for each group in the between groups ANOVA are gonna be potentially different. For within groups ANOVA, not necessarily so, because you would expect if each participant goes through each level, you have an equal number of participants in each groups. Overall degrees of freedom is basically the overall n-1. We talked about the F distribution. It's one critical value. It's a unimodal right-skewed distribution. You're comparing against the critical value on your x-axis, which is basically consistent with your degrees of freedom between and the degrees of freedom within. The F-score is calculated as between groups variability divided by within groups variability. We did that last time with the idea of essentially comparing each individual means by measuring their deviation of variability from the grand mean. You are able to get a relationship between this variability of the means from the grand mean to the variability within these groups, which this is a very nice way to actually look at this and visualize it. The aim of an ANOVA is essentially to populate this source table, and this is kind of, and we will see this today from R, the source table will always look the same. Whatever statistical software you're looking at, I've never seen a different format, so you will recognize the source table, whatever statistical printout you will get. It will always follow the same line layout. The components in the source table are also the same, irrespective of the software. So once you understood that one, you will understand or moving forward that you will see. Then we stopped last time. Okay, so here are the calculations in a bullet, in a table lined out. Again, between groups and over is basically for each individual X, for each individual entry in your overall data set. You basically calculate the group mean minus the grand mean squared. This is your variance between the groups. The X minus the M, the mean of the group, will basically squared, gives you the sum of squares and the variance within. And then you're basically getting here to the total variance, which is essentially each individual X minus that grand mean. That gives you the total sum of squares. Then carrying this on, dividing this by the degrees of freedom, here the second column gets you to your sum of squares, your variance for each of those dimensions, and then lastly gets you to an F. We did that with our dictator game example last time, and we have rejected our null hypothesis. Good. Then lastly, we spoke about effect size. So effect size introduces now a new metric, and you will find also an omega squared and a theta squared in the book, which there may be one or two questions, so familiarize yourself in principle what it is. Arithmetically, in words, it's basically a continuation of the so-called R squared. The R squared, when you look at it, you have a sum of squares between divided by the sum of squares totally. So when you look at that, you have a total variance and you have a between groups variance. What you do with this R squared, you calculate the proportion of the sum of squares between of the total sum of squares. So the R squared is essentially a proportion. And it will come again. So this proportion actually is the effect size. Because what you really want to understand, if there's a lot of variability in your total variability, you want to understand what part of that variability is actually by the differences between the means. So this is why it constitutes the effect size in ANOVA. So again, it's the proportion of the between sum of squares as a fraction of the total sum of squares. In regression analysis, it's also going to be called the proportionate reduction of error, because it basically constitutes the strength of a model and the explanatory power of a model, but more about that in next week on Wednesday. So R squared, keep that in mind. The omega squared is a continuation of the R squared, which basically is then further adjusted arithmetically for the degrees of freedom. And thereby it gives you a lower estimate of the effect size and means to account for the sample size within the sample. But basically we will not approach this arithmetically, but you have it in the books. Good. Conventions. We have a small effect size, we have a medium effect size, and a large effect size. We have small again from 0.01 to 0.06. So that's 1% to 6% is a small effect size. 6% to 14% is a medium-sized effect size. Everything greater than 14% is a large effect size. Meaning that from the overall variability in your data, a large fraction is being explained by the variability between the groups, thereby this having a large effect size in your ANOVA comparison. And this is where we stopped last time, post-hoc testing. So when the null hypothesis of an ANOVA is essentially that you have identical means amongst all groups. What the research hypothesis then logically is that at least one mean is different from any other mean, and you don't know which mean is different from which mean. So now you could again go and do multiple comparisons, but you again have the problem of statistical type 1 error that you're inflating with those multiple comparisons. Therefore, you have post-hoc tests. And these, you will only do post-hoc tests in 2 scenarios. So essentially, when you have a significant ANOVA and your F-score is larger than the critical value, then you will do a post-hoc test. The only time you will do comparisons without having a significant F-score is when you have a priori, quote-unquote, planned comparisons. So you enter your research question and you enter your analytic approach by knowing that you want to compare group 1 versus group 3 because that fits your research question. Then you will still do the comparisons, irrespective of the type 1 error risk. However, you can always do post-hoc tests, which is actually preferable to these a priori planned comparisons because they will kind of give you an adjusted, modified p-value. So a modified estimate of your type 1 error. So, so there are 2 most commonly used post-hoc tests. There are more than that, but these are the 2 that Norton and Heinzen present. So the first one is Tukey Honest Significant Difference Test. That's the Tukey HSD test. In the Tukey HSD, you're basically calculating the differences between all the groups divided here by your SM, which is calculated as your variance within divided by the sample size. So therefore you get this SM, which is kind of an estimate of your standard deviation to some extent. And by calculating this HSD, you calculate the Q. And the Q essentially is your difference. This is a modified p-value, so to say, and it's Q value. It's not a p-value actually, but it's a Q value, and you will compare this Q value here against this Q table. So that's the way how you're approaching this in a Tukey HSD test. So just know essentially when you have a Q calculated, where to essentially read and what, and then reject at the respective alpha level. That's number 1. We're not going to calculate this arithmetically, but basically the second one, and in my opinion, more commonly used one, is the Bonferroni test. And the Bonferroni test is basically a post-hoc test that gives you a stricter critical value. So it assumes a lower alpha. So you get the same p level, but you will basically use a different alpha level that is Bonferroni adjusted. We're basically assuming that this changes with the number of comparisons you actually conduct in your post-hoc comparison. So in our case, it's with the foraging, it was 6 comparisons, so we would use the p-value here of 0.008, which is substantially lower than the 0.05 that we usually used. So that's the Bonferroni. And that was the end of this. Any questions on the one way between groups and over? So I think the post-hoc testing is quite intuitive. So you're only doing this post-hoc tests when you have a significant F and a significant p-value after comparing it to an F-score, to a critical F. Then you will compare the groups within. And now to the actual main topic today. So as anticipated, we didn't get through the one-way between groups and over to an extent. So hypothetically, it should have been both. So today we're going to do the comparison in the one-way within groups and over. And then we're going to do a little R exercise, which is practice lab 4. Good. One-way within groups and over. So the arithmetics actually are the same. So, and you will see that they're really similar to what we did with the dictator game example. The only difference now is that we have the same participant undergoing each level of your independent variable. So you basically, you have somebody doing something multiple times, and thereby you get you basically you are able to account for these inter-individual comparisons and take this variability out and subtract that from your total variance. Thereby, you lower the denominator, and thereby you increase your probability to get a more accurate estimate of your F. It's also labeled a repeated measures and over, and it's most likely if you read it in papers, if you read about it in papers, you will read it as a repeated measures and over. So it reduces, bless you, it reduces an error due to, bless you, it reduces an error due to differences between the groups. Groups are identical for all of the relevant variables because each group includes exactly the same participants. So thereby you essentially get a pure estimate of these group differences. You're removing that from the total variability, and your effect size will automatically be larger. And whatever difference you see will really reflect the difference due to group differences. And you take some of that random variability out of the equation. And so you remember with the graphical displays of data, we talked about interpolation and extrapolation. So interpolation, inter always means there's something in between, whereas extra is something beyond what you actually have represented as data. So now I just want to introduce here inter and intra, because inter is between and intra is within one individual, right? So we are now determining the inter-individual variability between those groups, because it's between the groups, by basically incorporating intra-individual variability of each individual. So you're teasing this out, you're taking this out of the equation, and thereby you accentuate and you emphasize the inter-individual variability. Make sense?
Between which groups are we talking about?
Between the groups of whatever comparison you do. So each individual undergoes the same groups. You take this intra-individual variability out of the equation, and thereby you emphasize really the difference between the groups. So you're reducing your variability, as we will see arithmetically. So it reduces the within groups variability due to differences for the people in the study across the groups. Good. Calculations are the same, as similar to the one way between groups and over a subject sum of squares. So now we're calculating, in addition to that, we're calculating this intra-individual variability. So we're calculating what's the variability of one individual and try to estimate this and remove this from the overall estimate of the variability that we have observed. So a subject sum of squares is calculated in addition to the between groups, within groups, and total sum of squares. The subject sum of squares reduces the within groups variability by removing the variability associated with each individual participant's difference amongst all groups. So we're taking this out. The steps are the same. We identify the population, the populations, the distributions, and the assumptions. The assumptions are the same again. So normal selection, the random selection, normal distribution, and homoscedasticity between the groups. We're stating an R&D research hypothesis, which is again that none of these groups are different. Well, the research hypothesis is that at least one is different from another. We determine the characteristics of the comparison distribution. This is where we quantify the variabilities. We determine critical values or cutoffs. And this is here done, and I'm flagging this, it's done in the same fashion as we have done it with the F-score table with the one-way between groups and over, follows the same layout. So this subject sum of squares, you're just removing it from the overall variability, but the rest is absolutely identical. You calculate the test of this and make a decision. Yeah, well, there is one more assumption now that you need to make, because you have repeated measures. And so now let's go back to the paired sample t-test. And this is essentially an assumption that is more of a design question when you do such an experimental study. You need to make sure that there is no order effect, so that the order in which you define your independent variable, and we will get to the example of today, which involves the tasting of beer. So now we had wine tasting, now we do beer tasting. So essentially you want to avoid these order effects. So the order effect by beer tasting could be that maybe your judgment of a beer, when you judge the quality of a beer, is different after you tasted a really good beer or a really bad beer. So these are potential order effects, and we will talk about this in a second. And just like with the paired sample t-test, if you think that there will be an order effect, you counteract this by counterbalancing. And this is again where you have in a crossover design, you randomize the order in which each subject is approaching each level of the independent variable. So you're randomizing within that group allocation and which one is being started for each individual. And if you kind of can do that in a successful manner, you will minimize the effect of confounding due to an order effect. So again, the F distribution is a comparison distribution, and yep. So the example now, and this is referring now to the spreadsheet that is posted. So we have now on the spreadsheet one way within groups and over. We have now the estimates of the quality of 3 different beers. So there's a cheap beer, there's a mid-range beer, and there's a high-end beer. So, okay, Fallows wanted to know whether his recruits could distinguish amongst widely available American beers that were categorized into 3 groups based on based on the price. So you have high-end beers like Sam Adams, you have mid-range beer like Budweiser, and cheap beer like Busch. All of these beers are lagers, a type of beer chosen because it can be found at every price point. Here, data. Mean scores on a scale of 0 to 100 for each category of beer for 5 participants. So, so now we have here 5 participants that give you 3 different estimates of 3 different beers. So just like last time, we're going to do as the very first step, let's just quickly bring this into a long format. So we're doing the same exercise as we did last time, just that we're ahead of the exercise. So the only thing you need to do here, you just align it with the estimates. So you're copying those participant IDs down, that you have them 3 times. So now you have here beer grade. This is now the beer type. Here you have cheap. Here you have mid-range. And here you have high-end. So you can just fill this essentially. And that's how this should look like in the end of the day. So the idea is here again to have it organized in a format that kind of allows you to do your calculations with. And then we can just in the same format as we did last time, which is calculating the grand mean, which is essentially nothing else but the average of all these values. Then we need, so now we need essentially, we need more means, right? So we need now a group mean. Let's just get a little bit more space. We need now, first we need a group mean, which is just the average of each group. So that's our M, which is here the average of each of these groups. And when we look at these means already, we actually do not really find that much of a difference between cheap and mid-range beer, but we really find a difference to the high-end beer. So that's already interesting. So we can now just basically just fill out our data sheet here. So we know now that cheap beer has a mean of, these are the group means. So now here we would copy down 34.4. Careful that it's only the values. And then we just need to complete these all the way down. So it's just the same exercise we did last time. Yeah. So now we're completing all of this down. And that basically gets us the respective mean corresponding with each individual entry, right? Simple. So the next difference we need a subject mean. That gives us the variability within one subject. So now if we are calculating a mean for each subject, we can do this again in the same fashion. And here we get the respective subject means. The only thing where it's getting a little trick here is now we need to correspond the individual measurement with the individual subject. And that's simply done by making sure always the paste values, otherwise it's shifting. Good. So these are our subject means. So now we have the group means, the subject means, and the grand mean. So that's already pretty much all we need. Okay, so again, so we have 3 different types of beer that are being tested by 5 different individuals. We're calculating a group mean for each of our groups. We're calculating a subject mean for each of our subjects. So the group mean gets us the group within group variability. The actual, the subject mean gives us the individual variability for each subject. Now we want to test our null hypothesis that at least one of these means is identical. One of these 3 means is identical to another mean. So all of these are different, at least one of them is different, sorry, under the research hypothesis. Misspoke. So research hypothesis, at least one mu is different from another mu. And thereby we need now, next we need to quantify the degrees of freedom. So we need a degree of freedom between which is simple with 3 groups. It's 3 minus 1 is 2. Then we need the degrees of freedom subjects. So we know we have 5 individual. 5 minus 1 is the F subject. 5 minus 1 equals 4. Then we have degrees of freedom within. That's degree of freedom between, which is 2 multiplied by degree of freedom 5 minus 1, 4. So that's degree of freedom is going to be 8. So we have between multiplied by degrees of freedom subjects. So this is df within is, oops, 4 multiplied by 2, which is 8. And then with degree of freedom total is now n total minus 1. So we have here a total of 14 entries, which is 15 minus 1. So this is 15 minus 1 equals 14. And again, 8 plus 4 plus 2 adds up to 14. And that's important to keep in mind for the source table, because you will be asked for the homework to complete the source table or to complete source tables. And these relationships are important for you to complete these source tables and to make the right comparisons. So this is how you determine all your degrees of freedom. If you go to the F-squared table now, so we have set the degree of freedom in the numerator between groups. Degrees of freedom are 3 groups minus 1, so that's 2. And our within groups degrees of freedom is going to be 8. So this is the degrees of freedom between multiplied by the degrees of freedom subject. So that's 8. So we have 2 and 8 at a p-value of 5%. Is a critical F 4.46. So critical F equals 4.46. Good. So far, so good. So the fourth step is the same as identical for one way. So now we need to look up that critical value. And then we're going to get essentially already to the calculation. And I'm just carrying this over now. Did you follow along with what I am doing here in the spreadsheet? I hope some of you at least can follow along on the Excel spreadsheet. I know it's a little fast, but it is just unfortunately a lot of dense program today. So that's why I'm going a little faster than I did in the beginning. But these are basically our calculations. So once again, we need x minus gm squared gives us the sum of squared total. The sum of squares between is the m minus gm squared. Sum squared gives us the sum of squares for the between group variability. Then we have sum of squares subject. This is what I did here. So that's the m, and this will be subtracted from the gm squared. Gets us this as a sum of squares subject. And the sum of squares within is now the arithmetic resultant of the sum of squares total minus the sum of squares between minus the sum of squares subject. So once again, you have the sum of squares total. So that's the overall variability. You're subtracting from that your between group sum of squares, and you're subtracting from that also your sum of squares for the subjects. So this becomes part of your variability that is explained just by this variability between the subjects, and you're taking this out of your estimate of your variability and in your calculation of the F. So if we do this calculation now, we're getting now x minus gm squared, which is essentially the individual x, oops, parentheses, individual x minus grand mean of 40.53 gets you an individual x. You're squaring this, and you pull this all the way down, and then you sum it up. So your sum of squares total is now 2,117.73. So that's your SS total. It's simple, right? It's literally, it's the same that we did last time. So we have each individual entry. Just now I've rearranged it. It's now in a long format. You're subtracting this from your grand mean. You get your x minus grand mean, and you're summing this up, gets you to the sum of squares total. Next, we're going to do the sum of squares between. So that's m minus gm squared. So this is now our m from here. Again with parentheses. The individual m minus our gm that we need to again log in with a dollar sign, because otherwise it's going to change. We're squaring this. We're pulling it all the way down, not that far. So the sum of squares between is now the sum of all of these entries. Like this, the sum of all of these entries. So our sum of squares between is 1092.1333. And now lastly, we want to calculate our sum of squares subject. So this is now m participant, or subject mean, m subject mean minus gm squared. And this is the same outline. We're doing subject mean, this, again with parentheses, subject mean minus gm, like this, logged in with a dollar sign, squared. There's considerably little variation, it seems, except for one individual here. Once we sum this up, we're basically getting a subject sum of squares of 729. So now our sum of squares within is now considerably smaller. This, don't we need that? So our sum of squares within is now this total minus the between minus the subject. So this gives us sum of squares within of 295 following this equation. So we have the total, we're subtracting the between, we're subtracting the subject sum of squares, and we get to within sum of squares. So this is the whole calculation. So it follows the same layout and the same approach as last time. And now you just need to carry on. So you're basically calculating the individual variance by dividing your sum of square estimate by the degrees of freedom. And thereby you get an f between, which is your variance between divided by your variance within. You get an f for the subjects, which is basically the variance subjects divided by the variance within. And as a resultant, you get 2 f scores. But for hypothesis testing, you're only interested in this f estimate. So, but we want to pack this into an f score table. We want to pack this into a source table. So let's do this. So we have now source. We have SS between. We have between subject and within and total. So the sum of squares is now between is this, subject is this, within is this, and total is this. Degrees of freedom, we know for between it's 3 groups of B's, 3 minus 1 is 2. We have subjects as 5 individuals, and we know that 5 minus 1 is 4. For within, we have 4 multiplied by 2, that's degrees of freedom subject multiplied by degrees of freedom between, that's 8. And the arithmetic sum is 8 plus 4 plus 2 comes to 14, bless you. It's 14. And now lastly, we just need to calculate our variance, which is now MS, which is now for the between variance. It's this divided by this. For the For the subject variance, it's basically subject sum of squares divided by the degrees of freedom. For this within variability, it's this divided by this, which is 36. And for the total, it's this divided by 14, gets us 151. Now we need two F estimates. So we have the estimate for the F between, it's MS between divided by MS within, and the F subject is MS subject divided by within. Between is now this divided by this, and this, no. Subjects divided by within. So we have now subjects divided by within. The only thing we're interested in is the F score from the between groups. That's 14.8. And that is significant. This is larger than our critical F of 4.46. Thereby, we're rejecting the null hypothesis of all the groups being identical. And this is the source table that I'm essentially interested in. And so this will be part of the homework. So please study the arithmetic dependencies. You will also be seeing those on the courses. Any questions on the source table? Or was that more or less clear? The calculations are a little bit, yeah, no, this is a little rougher. It's the same layout, right? So you just need, just like we did with the ANOVA and with the calculation of the standard deviation, you really need to only know what are you subtracting from what and how often, essentially. So you know that each individual entry subtracted from your grand mean gets you to the sum of squares total. That's your total sum of squares. Once you have your group mean, which is basically just the mean of each of these groups, or each of these group means are different, but you need to propagate them as often as you have entries. And then you calculate this m minus the grand mean, you square it, gets you to the sum of squares between. If you have now, lastly, that subject mean, you calculate this for each individual at each condition, or each situation, each level of your independent variable. You get a subject mean, you're subtracting this from the grand mean, gets you again this variability. It gives you a measure of this variability from the grand mean. The guiding star is the grand mean, but everything will essentially be calculated in reference to that grand mean. And that gives you a measure of this variability of each individual entry that you're interested in. So you calculate those four different sum of squares, and then the rest is just an understanding of the source table, where you basically have for the within groups and over now an additional line where you essentially take into account that the subject takes a part of the total variability. And basically will remove, once you understand the subject, you can take this out and reduce it only to the comparison between groups and within groups. The R square is essentially follows the same layout. So here you have the sum of squares between as a fraction of the sum of squares total. But again, you're subtracting the sum of squares of a subject, of the subjects, and you're reducing your sum of squares total. So let's do this quick. But basically the conventions are the same. So your R square here is sum of squares total minus parentheses, never wrong. It's between divided by sum of squares total minus sum of squares subject. Also keep in mind, by incorporating this, when you think about this arithmetically, so you get now here an estimate of an R square of 0.78 or 79. So that's very large effect size. So there's a very large difference between the groups, so to say, and this group difference accounts for a lot of the variability that you're seeing. And that's also shown here already when you look at the different means. So you see already that these two are likely not different, whereas this one really makes a difference to the grand mean. So that's a very large effect size. The conventions call for everything greater than 14% as being a large effect size. Now we can quickly do Tucky. Okay. So let's do a Tucky. If it asks you for that. Okay, so we do Tucky on a significant difference test. So if we do Tucky, we're basically calculating now so if we calculate now, so we need for 3 groups, we need M1 versus M2, we need M2 versus M3, and we need M1 versus M3. So this time we only have 3 groups, so it's a little bit less involved. So if we are calculating now our SM, so SM is here MS within square root of MS within square root of MS within divided by the N, which essentially is 5. Gets us an SM of 2.7. So if we're taking on now M minus 1, M1 minus M2, that's 34.4 minus 34.6 divided by 2.7. That's minus 0.06, or 7.74. Now we do M2 minus M3, M2 minus M3 divided by 2.78 square rooted gets us to an Q. Oops. Oops, I'm bracket. No. Oops, but no. No. Okay, let's do this again. SQRT. M2 minus M3, M2 minus M3 is divided by our SM within, bracket closed. So whenever you have something in a square root, you always got to make sure that it's positive. So there's no square root of a negative number, as you know. So if you subtract a larger number from a smaller number, you get a negative value. If you have that in the square root, it's going to give you a hiccup. So that was what happened to me. So now you have SQRT. And the direction doesn't play a difference when it comes to the estimation of the Q. So you have M1 minus M3. So we do M3 minus M1 to avoid this from happening again. Divided by the SM. No. divided by SM gets you 2.58. So looking at this now in the Q table, which we have here on the ANOVA with between. So here you essentially see you can basically compare these. We don't have the right Q table. We only have 2 levels. But basically, these are the Qs that you would then compare against your Q table. And based on that, you would basically see that there are differences. So you see that the Q is larger when you have M2 minus M versus M3 and M1 versus M3. And then you would just need to compare this against the Q table that I wish Norton and Heinzen would have provided us with, but they didn't. So this is the ANOVA within groups comparison. Any questions on any of this? I know it was quite a bit and it's quite complex, but I think the calculations, if we go step by step and you just understand the calculation of the sum of squares that gets you to the variance, this will essentially be a good pathway for you to tackle all questions. Any questions? If not, then we can lastly speak about weird samples. WEIRD actually stands for Western Educated, Industrialized, Rich, and Democratic. So I'm not really sure why this is in here, but there are some questions on the quiz, not many, but please make sure that you understand what you're looking at. That just basically means that you understand the demographics and the country from which you have sampled your individuals, and that you're basically understanding what makes this hypothetically different from other populations that you may be studying moving forward. So it basically goes back to constraints on a generality statement, whether you actually can generalize these study results that you have at hand when you study them in a Western educated, industrialized, rich, and democratic population, whether you can extrapolate them and actually generalize them to populations that you will find otherwhere in the world that are not Western educated, industrialized, rich, and democratic. Yeah, so these are weird samples. And the good reporting practices basically ask you to have constraints on a generality statement where you actually say that this was sampled from a population that has all these attributes. Should be standard. So you would basically report anywhere where you have sampled your sample from. So you would clearly declare this in your paper moving forward. So this was ANOVA within groups and between groups. Now, lastly, let's go and open our R. And you have the solution script posted on your canvas. There's a little bit of a caveat this time around because we are installing packages now. And that happens after you ran, again, control and return. You first clear your environment and you then install 2 packages in line 5 and 6. And this will take a little bit. And you will see down here that as soon as you ran these, something is happening. And this is the installation. So basically it queries a server online, it gets the required package, and it will automatically install this on your R.
Can we download the file that says solution? Yeah.
Yes. So once this happened, so these are actually 2 very useful packages. So moving forward, those of you that are maybe inclined to use R again, you will basically definitely need the dplyr package, which I warmly recommend. For those of you that are analytically inclined, please absolutely work with dplyr. And if it asks you, do you want to continue and use this to compile, your answer was why.
Wait, I have a question.
Yes.
I just downloaded it and it says like a yellow thing, packages and whatever required but are not installed. Yeah. So
These are these two lines.
so what should I do?
Either you click install where it says, or you run line 5 and 6. Fine.
Like, how do do you just do control F?
Yeah, just try and control it and then go down to line 5 and 6.
Just on line 5?
Yeah.
But then it keeps never stops.
No, it will stop. It will stop eventually.
Is it normal? I feel like
Yeah.
Yeah. Okay. Yeah.
Okay.
Mine doesn't know
The what?
I think it's. Mine looks like this. Is this gonna be a virus?
That's good.
Oh, no. Yeah, the TV doesn't have like on top of. Oh, yours just keeps running. Oh.
So once this ran through, once this has finished compiling these and installing these two packages, you're basically done. So this will use a different time. It may take a little longer for some.
Will this take up a lot of storage on our computer?
No.
Okay.
It's minimal, very minimal.
It does.
So it depends on your operating system how long that takes, but it shouldn't take too long.
Okay.
It takes a little unnecessarily long on mine, I have to say. You're done? Good. Good.
Mine's still going. Mine's in red right now. They don't know.
Which line am I supposed to be on?
Yeah.
So
How do I know when mine is done?
it's soon gonna be done.
The downloading.
Oh, but sometimes,
mine's
yeah,
still
yours
going.
keeps going.
It says it's done.
Good.
Mine doesn't.
Once it was done, and this is important, go then to line 5 and 6 in the beginning and make a hashtag. Once it's done, you hashtag it out that it doesn't have to run this again. Because when you hashtag it out, you comment it out. Just hashtag in front, then it turns green, and then it's commented out.
Is this done?
Yes, you're done. Okay. Once it's finished, please go up to line 5 and 6 and make a hashtag in front of these
Did you download? Yeah.
two commands. Yes, good. Yes, Kira.
Wait, how come mine? I don't know your mine.
You have what?
I don't have anything on mine.
Why is mine burning?
You have what?
I don't have anything on mine. Oh, mine's not empty.
You do.
Wait, my thing is this?
So now go to line 7 and 8, run these two library commands.
This is all there.
This one. That's just from last time.
Wait, how do you get everything down on the bottom? What are you doing?
Download that one.
How do you get everything to package?
Well, you just start 5 and 6, right? It automatically installs it. Yeah, correct. So install the packages is the command, how you run and install these packages.
How do we put a hashtag in front?
Because once you ran it once, you don't need to do it again. Then it's installed. And then you basically, okay, everybody focus, please. Once you have installed the packages, you hashtag it out. And then you just need lines 7 and 8 with library deploy and library R statics, where you basically call this library to be loaded. So now you just do this. It tells you library deploy, it runs it through, and now it's basically active. That's how you activate your libraries. Both of them. Good. Once you have done that, you're basically going on line 12, which establishes now our dictator game data frame. Then you go on line 16 onwards, so line 16 to 18 actually allows you to create DF2. So DF1 is now the dictator game, that data set that we played around with on Monday, last week on Wednesday. and DF2 builds our beer drinker example. So these are the actual data frames that we have used. And now, and this is the reason why we installed dplyr, because dplyr is actually a wonderful tool allowing you to summarize your data frames with something that is called a pipe, which is a percent smaller percent sign. And this being said, this is actually a nice grouping code where you essentially can quantify your summary statistics for your big data game. Yes, highlight 21 to 25.
And then control enter.
Control enter, yeah. You can do the same exercise with 27 to 31. You get the estimates that we have calculated for our beers. You can do the same by grouping it by participant. So the code, I'm not going to go too deep into the code, but basically what you see here by group by, you're grouping DF2 as per the participant. You pipe it into summarize, which is a summarization code. You say then, I want the count, which we have here. I want the mean, which we have here. And I want the rating standard deviation, which we have here. So that's a summarization code, right? Yes, 33 to 34 gives you the participant summarization. Gives you now a summary.
33 to 37.
Yes, gives you a summarization for the participant. And now remember all these laborious calculations we did for the ANOVA. And now we're doing the first ANOVA for the big data game. And this is your ANOVA. This is the ANOVA source table that you will get from R. You get the society estimate, which is a between group estimate. You get sum of squares, you get a mean square, you get an F value, which we calculated, and a corresponding P value. And you get here the residuals. The residuals are basically your sorry, excuse me. That's your variance within. So that's the source table in R. The same you can do with your within groups ANOVA, which is basically the second code here, which is ANOVA to 44 to 45. Gets you here the beer type, degrees of freedom between the beer types, gives you an F score, gives you a P value, and basically gives you the same results we calculated in Excel. Post hoc testing, Taki HSD gives you here an overview between the respective comparisons.
Did you choose 49 or 49?
That is line 49 and 50, yes. No, only 49, sorry. Only 49 for now. Doesn't matter, doesn't matter. So this is Taki. This is a group comparisons. This is a group comparison, foraging versus farming, industrial versus farming. So it's basically group and group-wise comparing the means. Gives you a Taki. Pairwise t-testing, that's a little trickier because here you have a grid where you essentially have an adjusted p-value for each of these comparisons. The way you're reading this is you have like farming, foraging, industrial here, farming, foraging, industrial here. And you basically have a comparison between farming and foraging. It's no different. P-value is 1. Foraging was industrial. So you basically have to compare them columns versus rows. Good.
So should we run 52?
Should
we run 52?
Yeah, just run this down. And then lastly, we have 52. We have a comparison of the beer drinking example. We have here the actual differences. This is again a pairwise Bonferroni, allowing for you to compare these beer types. Good. 4 last minutes. I'll quickly walk you through how to solve the practice lab number 4. You press control, you click in this first in the console, Control and L. You clear this entire thing. You click in the script. You press Control and A. You press Control and Enter. You run it all, but make sure that 5 and 6 were commented out, that you don't install the whole shebang again. Correct. And now you just select the whole thing. You Command and C the whole thing. You go in the Spotlight. You write your text edit. Once again, you are going in the text edit. You open a new document. You copy your console printout in there. You go on File, Save, and you save it as STAT1021 with your family name. And the clarification and the label of Practice Lab 4. This is your deliverable and this is what you need to submit. Thank you very much. Have a nice evening.
Are you able to show me how to fix this so that I could do it? Because